morning. Welcome to another episode of SUPA Chemistry. Today we're going to work with some basic atomic structure. A lot of this stuff is actually review for you guys. We'll be talking about how to calculate protons, neutrons, electrons, some basic stuff about those different particles. Eventually we'll get into some atomic mass stuff and talk about mass spectroscopy. So that's kind of the plan for today. So what I want to start with is just let's make a little chart here. And this is electrons, protons, and neutrons. And let's just put symbol here. This is going to be absolute charge. And this is in coulombs. And we have relative charge. We have absolute mass. That's in grams. And then let's have mass in AMUs, atomic mass units. Okay, so I just want to run through these different things because you do need to know these for each of the protons, neutrons, and electrons. Symbol for an electron that we're going to use, E with a minus sign. Proton, we'll use a P. Neutron is an N. Pretty simple. Now, this is absolute charge. This is the actual charge of each one of these particles. So an electron is negative, and it has a negative 1.602 times 10 to the minus 19th charge. And then a proton is the exact opposite of that, positive 1.602 times 10 to the negative 19th. And then neutrons are still neutral. Okay, so this is absolute charge. Relative charge is relative to each other, so that we say an electron has a minus 1 charge, protons have a plus 1 charge, and neutrons are still neutral. Now, the absolute mass is in grams, so the mass of an electron is 9.109 times 10 to the minus 28th. It's extremely small. Extremely, extremely, extremely small. Proton, much bigger. 1.673 times 10 to the negative 24th. And a neutron is about the same size as a proton, 1.675 times 10 to the minus 24th. Okay. So you need to be able to convert grams to AMUs. 1 AMU, here's your factor, equals 1.66054 times 10 to the minus 24th grams. That's a 4. Right. Now, depending on sig figs, really depends on how many of those digits you need. Right. So now, if we were to do these conversions, an electron has a mass in AMUs of 5.486 times 10 to the negative 4th. Proton has 1.0073, and a neutron is 1.0087. And those are in AMUs. Now, in reality, the mass of an electron is equal to 1/1836th of a proton. It's extremely small. That mass of electron is extremely small. Matter of fact, it's so small that we say it has no mass. In reality, it does, all right, but it's so small that we say that an electron has zero mass. All right, so if an electron has no mass, that tells us that all the mass of an atom is in the nucleus. Good. And we know that our protons and neutrons make up the nucleus. Together, these are called the nucleons. Okay, so the nucleons are the protons and neutrons. All right, so we need to be able to calculate these for each element, or each atom. All right, so our atomic number tells us the number of protons and the atomic number, the number of protons, tells us what element it is. So if I go out into the field out back and I dig up an element, let's say I dig up some element and I test it, and it has 19 protons. Well, if it has 19 protons, it has to be potassium. So the number of protons, or the atomic number, tells us what element it is. The atomic mass calculate that atomic mass, it's the number of protons plus the number of neutrons in the nucleus. Okay. So if we were to look at potassium, it has an atomic number of 19 and a mass of 39. Okay. So we can actually calculate the number of protons and neutrons right from here. So to calculate neutrons, if you remember, we take the atomic mass minus the atomic number. So for potassium, we would take 39 minus 19, and we would get 20 neutrons. So I should be able to basically give you any atom and ask you to calculate protons and neutrons. So okay, I could say, hey, calculate protons, neutrons for beryllium. Protons, we'd look up the atomic number, okay, 4. Neutrons, look up the atomic mass, subtract, that would give us 5. Okay, you should be able to handle this, no problems. Next place we need to be able to go is into electrons. If an atom is electrically neutral, In other words, it has no charge. What that's telling us is the number of negative charges is equal to the number of positive charges. So that tells us that the number of electrons has to equal the number of protons. So if I have an electrically neutral atom, the number of electrons equals the number of protons. Okay, so if we come back up here, okay, this is an electrically neutral atom. If it was an ion, it would have a charge here. Alright, so if it was an ion, it would have a charge. There is no charge, so this is electrically neutral. So the number of electrons is going to equal the number of protons. Alright. Well, what if we have an ion? Remember, an ion is an atom or group of atoms that have gained or lost electrons. Remember, we cannot gain or lose protons and neutrons from the nucleus. The only particle we can lose from the atom is an electron. Alright, so we have two types of ions. We have cations. These are our positive ions. Okay. If it's a cation, that tells us that it has lost electrons. And then we have anions, which are negative ions, which means it's gained electrons. So if we have ions, well, here's an example. Let's say we have K+. This is telling me that it's a cation, and that this atom has lost electrons. Fluorine -1. This is an ion. It's telling me this is an anion, and that it has gained electrons. Now I suppose there's a formula for the number of electrons in an ion. The number of electrons is equal to the number of protons plus or minus the number of electrons lost or gained. So if we look at K+1, this is telling me that it's lost one electron. Normally potassium has 19 electrons. It's lost one, so it would have 18 electrons. Let's calculate protons, neutrons, and electrons for a magnesium cation with a +2 charge. Well, protons are the atomic number, which is 12. Neutrons, mass minus atomic number, so 24 minus 12 is 12. Electrons. Now normally, if this was electrically neutral, protons would equal electrons, so it would have normally 12 electrons. This is telling us that it's lost 2 of them, so it would have 10 electrons. Alright, now there are a couple other things that we should include here. Net charge. If you're asked for the net charge, it's whatever the charge is of the ion. Okay, so net charge for this would be +2. Nuclear charge. Nuclear charge is just the charge of the nucleus. Maybe we should write that. Nuclear charge is the charge of the nucleus. Now, what particle in the nucleus has a charge? Only the protons. So really what the nuclear charge is just the number of protons in the nucleus. Alright, so this has 12 protons, so the nuclear charge of this ion would be plus 12. Alright, why don't you try this one? Okay, go ahead and do this. So I'm just going to pause. I want protons, neutrons, electrons, net charge, and nuclear charge. Alright, I'll give you a minute to do that. Alright, so we use our periodic table. Okay. And please use the one that I've given you. Alright, so on the reference section of Google Classroom, I've posted your periodic table. So please use the one that I gave you. Protons, same as the atomic number. Alright, so the atomic number of nitrogen is 7. Neutrons is mass minus atomic number. Mass is 14 minus 7, which means we have 7 neutrons. Normally, if this was electrically neutral, it would have 7 electrons. This negative 3 charge tells me that it has 3 extra, so this has 10 electrons. Net charge. Net charge is whatever the charge is of the ion, so it would be minus 3. And the nuclear charge is the charge of the nucleus. It has 7 protons, so it would be positive 7. Hopefully you did okay with that. Alright, let's talk about isotopes. These are 2 or more atoms with the same number of protons but different number of neutrons. That is the definition of an isotope. Now, because they have a different number of neutrons, as a result, the atomic mass is different. I will caution you, okay, if you say an isotope is the same number of protons, two or more atoms with the same number of protons but different atomic mass, it will probably get marked wrong, and they may list that in a multiple choice question. Alright, that's not the definition of an isotope. Okay, it has different numbers of neutrons, and that different numbers of neutrons actually is what causes the atomic mass to be different. Okay. So, probably the most famous isotopes are carbon-12 versus carbon-14. Right, so they're the same element, okay, because they have the same number of protons. they differ in the number of neutrons, which is what changes our mass. So let's go ahead and calculate protons, neutrons, and electrons for each one of these. Well, if we look up carbon, its atomic number is 6. Okay. They're both carbon, so they're both going to have 6 protons. If we subtract, 12 minus 6 is 6 neutrons for carbon 12. Carbon 14, 14 minus 6 is 8. They are both electrically neutral, so they each have 6 electrons. So the difference between these two atoms is the number of electrons. Oh, excuse me, is the number of neutrons, which was what makes them isotopes. Okay. This weird number of neutrons is actually what makes this radioactive. And we'll talk about that eventually, okay, why that happens. Okay, so isotopes are same element, same number of protons, different number of neutrons. Okay, so if we look at, let's say we have boron. If we look at boron, its mass is 10.81. So we can take a guess at what are the isotopes that are involved with boron. All right, there has to be, because remember this is an average. We're actually going to talk about this in a minute. All right, this is an average. So this means that there has to be probably a boron 10 and a boron 11. Right, probably. Right, if we were to guess, one below this number, one above it. Right, those would be the isotopes of boron. Right, and they differ by 1 neutron. Let's talk a little bit more about the atomic mass. It is also called the atomic weight. And the atomic mass is the weighted average of all the naturally occurring isotopes of that element. So if you look at your periodic table, okay, so let's go back to boron. This is the atomic mass. It's a weighted average of all the naturally occurring isotopes of boron. Okay. Now, how many atoms of boron have this exact mass of 10.81? The answer is none. Okay, there is no boron atom that has a mass of 10.81. Okay, this atomic mass, or this atomic weight, is the average of all the different isotopes of boron. And I believe there's only 2. So atomic mass is expressed in AMUs, which is atomic mass units. And maybe we should write that in here. We should probably talk a little bit about an AMU. Atomic mass unit. And it's, for those of you that don't remember, maybe you didn't learn this, it's based on the element carbon. An AMU is based on the element carbon. Actually, it's based on carbon-12. And 1 AMU is 1/12 of an unbonded carbon-12 atom. It's 1/12 the mass of an unbonded carbon-12 atom. Okay, so that's how we denoted, or that's how we came up with this atomic mass unit. You need to know that. So how do we come up with this weighted average? So our weighted average mass is equal to the mass of the first isotope times what's called our percent abundance of the first isotope plus the mass of the second isotope times the percent abundance of the second plus the mass of the third times the percent abundance of the third. Right, so however many isotopes there are for that element. That's how we calculate this weighted average mass. So let's try a couple problems here. So carbon has 5 naturally occurring isotopes. Here's carbon-10, carbon-11, carbon-12, carbon-13, and carbon-14. Now, if we look at a sample of carbon, okay, these come in these break down into very specific ratios. Now these numbers are rounded, just so it's for simplicity. If we look at a sample of carbon, 1% of that sample is carbon-10. 8% is carbon-11. 81% is carbon-12. 9% is carbon-13, and 1% is carbon-14. These are my percent abundances. Okay, these are the percent abundances for each one of these isotopes. Right, now this is a weighted average, so it pulls it towards the one that's most abundant. Okay, so the most abundant by far is carbon-12. So when we do a weighted average, it pulls the average towards the one that we have the most of. All right, so we're going to expect our weighted average to be somewhere near 12. All right, well, our weighted average is equal to the mass of the first isotope times the percent abundance of the first plus the mass of the second times the percent abundance of the second plus, and I could write it all out, but I'm not going to write it all out. Okay, so here we go. Our weighted average is the mass of the first times the percent abundance, and remember we can't work in percent, so we have to convert this to a decimal, so it's 0.01, plus the mass of the second times 0.08, plus the mass of the third times 0.81, times the mass of the fourth, which is 13, times 0.09, and then finally 14 times 0.01. When we do that, all that math, we end up with 12.01 AMUs. Okay. Now that's not exactly what's listed on your periodic table, and the reason why is because the percent abundances were just rounded, so we could do some easy math, right? But that's close, right? But that's how these are calculated. That's how we calculate our weighted average. Alright, let's try something a little bit different. What is the percent abundance of vanadium 50 and vanadium 51 if the average atomic mass is 50.9415? Now, hopefully you recognize this form of writing an element. Okay, so this is mass. Okay, so if this is the element, this is the mass. It's just another notational way to write our element. All right, so these are isotopes. They differ by a neutron. All right, so we can actually calculate. Our percent abundances. Now, this trick only works if there are two elements. If there are more than two, you're going to have to do something a little bit different. All right, so if we look at our formula, weighted average equals the mass of the first times the percent abundance of the first plus the mass of the second times the percent abundance of the second. All right, now just by looking at the average atomic mass, we know which one's going to be which one there's going to be more of. Okay, this is pulled way up towards 51, so most of this has to be vanadium 51. So now we just substitute. Okay, so the mass of our first is 50. We don't know our percent abundance, so let's just call it X. The mass of the second is 51. I can't call this X because we've already defined this as X, but remember, if we were to add our percent abundances up, okay, and remember these are in decimal form, they have to equal 1. So if there are only two, I can say that this one is 1 minus X.